with useful libraries, algorithms, LLMs, supervised learning, neural networks, reinforcement learning, and more. Welcome to Crazy Fast AI and ML 101 tutorial. We continue here our SuperFast course, in which previously I've shown you how to start working with Anaconda, Python, Jupyter, etc. More than 30 classification techniques like CNNs, RNNs, transformers, GPT. Here you'll see a couple of regression, unsupervised and semi-supervised algorithms, and in the following you'll see reinforcement learning techniques, and more about LLMs like ChatGPT, Claude, Copilot, etc. You can find this tutorial at my site, superai.pl. At the moment you watch it, it might look a little different than here, but it'll be mostly the same. If you haven't seen previous parts of this tutorial, you might want to check those first parts, where I show you how you can start working with Anaconda, Jupyter notebooks, etc. And where I show you in more details the first two algorithms. Okay, now, something important for your safety. Be advised, because there will be a lot of fast-changing pictures in here. If it's too fast, you may slow it down or even stop for a moment. So let's start this kind of fast tutorial. See how long you'll last. Just be safe and don't overdo it. And here we go. Have fun. Regression is a type of machine learning task, where the goal is to predict a continuous numerical value based on input data, unlike classification, which predicts discrete labels. Regression involves finding the relationship between the input variables and a continuous output. Common regression algorithms include linear regression, decision trees, and more complex models like support vector machines and neural networks. Regression models are evaluated using metrics like mean squared error, MSE, or R squared, which measure how well the model's predictions match the actual values. Regression is widely used in various fields, from predicting house prices to estimating stock prices or forecasting sales. So let's see the regression algorithm in work. We'll start with an example of decision tree regression with Scikit-Learn in our Scikit-Learn environment. In the first example, a decision tree regression model is created using Scikit-Learn, trained on a small dataset of input-output pairs, and then used to predict the output for a new input point. The second example generates a random dataset, fits two decision tree regressors with different maximum depths, and visualizes the predictions alongside the original data, to illustrate how model complexity affects regression performance. In the third example, the diabetes dataset is loaded, split into training and testing sets. A decision tree regressor is trained on the training data, and various metrics, like R-squared and mean squared error, are calculated to evaluate the model's performance on the test set. And that's it. Now let's move on to linear regression. Here, in the first example, we use Scikit-Learn's linear regression model to fit a simple dataset of input-output pairs, and extract the model's coefficients to understand the relationship between the input features and the target variable. And in the second example, we generate a more complex dataset with two input features, fit a linear regression model, and evaluate its performance using the R-squared score, while also extracting the coefficients and intercept to describe the linear relationship. Finally, we make a prediction for a new input point, demonstrating how to apply the fitted model to unseen data. Both examples highlight the process of building, fitting, and evaluating linear regression models using the Scikit-Learn library. In the third example, we load the diabetes dataset, split it into training and testing sets, and then fit a linear regression model to the training data. The model's performance is evaluated by making predictions on the test set, calculating the R-squared score, and computing the mean squared error to assess the accuracy of the predictions. This can be used for predictive modeling in healthcare, specifically for predicting the progression of diabetes based on various health-related features. Now let's train an SVR model. Here in this first example, a support vector regression model is created, trained on a small dataset, and used to predict the output for a new input point. In the second example from Scikit-Learn's site, a synthetic dataset is created by generating random input values and their corresponding sign values, with added noise to some target values, and three different support vector regression models, RBF, linear, and polynomial, are trained on the data. The results are visualized in a subplot grid to compare how each kernel function fits the data, with the support vectors used by each model highlighted, to demonstrate their impact on the regression. And in this final improved example, the diabetes dataset is loaded and split into training and testing sets for model evaluation, and three different support vector regression are trained on the training data. The performance of each model is then assessed on the test set using metrics such as R-squared, mean squared error, and the model score, which are printed out for comparison, to determine each model's effectiveness in predicting diabetes progression. Next, we use the random forest regression model with two examples: the AdaBoost regressor and the gradient boosting regressor with Scikit-Learn. As you can see, all these examples, originating from Scikit-Learn's site, are very similar and easy to use and modify. Have fun modifying them to suit your needs. Our next model is an ensemble regression method. In these two examples from Scikit-Learn's site, we train and compare the performance of three regression models: gradient boosting regressor, random forest regressor, and linear regression, on the diabetes dataset. In the first example, we visualize the predictions for the first 20 samples from each model, along with those from a voting regressor that combines their predictions. The second example splits the dataset into training and testing sets, trains the models on the training data, and evaluates their performance on the test data, by plotting the predictions, and comparing their R-squared scores to assess how well each model generalizes to unseen data, with the voting regressor's performance also evaluated for comparison. Next we test multi-output regression with Scikit-Learn. That involves predicting multiple target variables simultaneously, by extending a regression model to handle multiple outputs, which can be achieved using models like multi-output regressor, that wrap any estimator to support multi-output problems. Here we first create an array with multiple target values. Then, a synthetic dataset is generated with three target variables, and a multi-output regressor is instantiated. The model is trained on the generated dataset, X and Y, and predictions are made for the same input data, X, enabling the model to handle multiple target variables simultaneously. Okay, now let's try neural network regression with TensorFlow. We'll go for that to our TensorFlow environment with version 2.16, and install two new libraries, Pandas 2.2.2, and Seaborn 0.13.2. We load the AutoMPG dataset. That contains information about various cars, including features like engine specifications, weight and model year, and can be used for regression tasks to predict fuel efficiency, MPG. Based on these attributes, we prepare it for training and visualize the data. We normalize the data to ensure that all features have a similar scale, which improves model performance. We then train multiple models for the same task, predicting the MPG, fuel efficiency, from car attributes, using different approaches, a simple linear regression model, a horsepower-specific model, and a deep neural network model. After training, we evaluate the model's performance, visualize the results, and save the best model for later use, ensuring that we understand and compare how each model handles the prediction task. By the way, as you can see, this example from TensorFlow's site was created by Francois Cholet, who is also the author of the highly interesting book Deep Learning with Python. If you're interested, you can check out TensorFlow's site for more information. Meanwhile, this concludes our quick overview of regression techniques. So now let's talk about unsupervised and semi-supervised learning. Unsupervised learning is a machine learning paradigm that deals with unlabeled data, where algorithms learn patterns and structures without predefined categories or outputs. To guide the learning process, it aims to find hidden patterns or intrinsic structures in the input data, often using methods like clustering, such as k-means, or dimensionality reduction techniques like PCA. Semi-supervised learning, on the other hand, combines a small amount of labeled data with a larger pool of unlabeled data, improving the model's accuracy by leveraging both types of data. This approach is particularly useful when labeling data is expensive or time-consuming, as it requires fewer labeled examples but can still achieve strong performance. While unsupervised learning focuses on discovery and pattern identification, semi-supervised learning combines both knowledge from labeled data and discovery from unlabeled data, enabling better performance in tasks like natural language processing and image recognition. We'll use Scikit-Learn environment for both of them. As an example of unsupervised learning, we will use k-means clustering with Scikit-Learn on the digits dataset, which consists of images of handwritten digits. Clustering groups similar data points based on their features without prior labels or categories. In this case, k-means clustering will partition the dataset into a predetermined number of clusters, each representing a distinct digit. By applying this algorithm, we can explore and visualize the inherent patterns in the data, allowing us to identify how well the model groups similar handwritten digits together. This approach is particularly useful for tasks such as image segmentation and pattern recognition in large datasets. For semi-supervised learning, we'll use label spreading with Scikit-Learn on the iris dataset. In this example, we first create a set of labels, where approximately 30% of the data points are randomly assigned as unlabeled, and then we fit the label spreading model to the dataset, allowing it to propagate labels based on the structure of the data. Finally, we evaluate the model's performance using the score method, which provides an accuracy measure of how well the model predicts the species of the iris flowers, based on both labeled and unlabeled data. In this case, the output accuracy is approximately 66%. And that concludes the regression, unsupervised and semi-supervised learning part of our tutorial. I hope you found it helpful. If you'd like to explore these methods further, visit the sites with the examples we've used here. You can modify the examples, experiment with different datasets, or try other libraries. With each change, you'll deepen your understanding of the topic. So good luck and have fun. Meanwhile, the next major task in machine learning is reinforcement learning, which we will explore next. But for now, let's take a break. And thanks for watching this. You will find the next part of this tutorial on my YouTube channel. And if you want to get notifications about the newest videos I make, hit that subscribe button. Once again, thanks for watching, and remember, improve yourself, improve your business, improve the world, but also live and have fun. Yours, Super AI.